Okay, so today our first topic is basically, so we will look into some data cleaning logic with NLTK, and then some data preparation with SciKit Learn, and then we'll quickly go through this bag of word model and then word embedding. Then, then you guys are more than welcome to jump in any point of time. So let me, okay, let me, okay, so, let me open the code and I'll share my screen. So I'm going to open some sample code that I have for the study group. Okay, so also there is, can you just see my screen?
Yes, no.
Okay. Yeah, so, okay, so the first thing is we look into some very basic stuff with for text cleanup with NLTK. So I'll put these things in GitHub and I'll share the GitHub link with you guys. So basically, like if you with the file, if you look into the file, there is the installation steps I have written down, so you can follow that and install in your computer. So I'm using Mac, so I don't know how, if you guys have Windows, the installation step might change. So I'm not sure about that at this point because I don't have Windows. So like some very basics. For example, if you have a text, like any text, then so there is a function called word tokenize. So it will basically just split the word, and you can, if you print this, you will basically see the only the words. So I'll show everything, like I'll comment out and I'll show you one by one. So just now, like we are basically like just reading the words. So if I run it, then you basically see that it's just nothing. So it basically has like all the words. And the interesting thing is you have the dot, like the full stop, it's also counting that as a word, which is funny. So if you want to have like you don't want to have, because dot is not a word. So what you can do is basically you can use like, you can only look into words that are alphanumeric, alphabet basically. So if you run this, you'll find this. So for example, the previous one has like dot the result, and this one only has, like if you look at the second result, there is no dot. So it's actually finding the, it's only showing the alphabetical words, which doesn't have any like basically dot or any other non-word basically. So so I think there's a question. There is a question. I lost the chat log. Where is the chat? The question is, so I think there are a couple of questions. So I think the question is like, if there is like any apostrophes, what will happen? So like in this process, it will not. I mean, it will. I think it will remove the apostrophes. So I think in this case, I don't know what will happen. Let's. This is a good point. Let's include this in the string and see what happens. Right. We can do that. Okay. Suppose we do this, right? So let's see what happens, right? So in the first output, this is, I mean, so in the, let's see what happened in the first output, where it's just tokenizing. It's making Bob one word and apostrophe S another word. I don't know why they make it. If you ask me the reason, I don't know. And in the second case, when we are doing only like is alpha, it doesn't even have apostrophe S, so it's only taking Bob. So that's I don't know how to explain this. Like, if you guys know, like, let me know. Like, I don't know. So, does anybody know this? Like, why this happens? Because Bob's, depending on like what you are doing, I guess that should be one word. And okay, the other thing is, okay, so let's comment out a few more things. So if you look at this sentence, this has like a lot of these is, and like if you have like a huge high volume of text, there will be a lot of these is, are, and those type of words which are not, it doesn't really convey anything. So those words are called stop words. So you can actually tell, you can specify in NLTK library to say like what are the, print out all the stop words in the English library. So for example, if we print out English words, in this case, then it will be like this. Okay, why it is not showing this one? This should show the stop words. For example, if I don't print these things, this should print something. Yeah. So basically, I didn't save the changes, so it didn't show. So now you can see like all the stop words in English. So if you want to avoid, for text processing, if you want to avoid stop words, then you can specify that for your text processing. So that's one, and the other thing is, the final thing is this that we'll look into. So for example, if you think like dog and dogs, they both have the same stem. Stem meaning basically root. So somebody asked me like, what is stop words? So stop words are basically like I, me, in, out, is, and, or, like, so those are kind of like joining words. Yeah, so those are like very frequent words which doesn't really convey. I mean, they're like joining and all, but if you want to count words, then it's kind of like, it doesn't give you a good idea of like which word is more frequent, because those words either way come to make a sentence. They really don't make any like anything significant, right? So yeah, so stop word and then like stem. So you can so there are different algorithms to find the stem from a text. So Porter stem is basically one type of algorithm. I think there are a couple of other stemmers that stem the words. So for example, we can look into this. Let's see what happens. For example, here it is saying that, for example, if you look at interesting, like interesting, yeah, so yeah, there is a central repo. I'll share the GitHub link with you guys at the end of the meeting, and the code will be basically there. So yeah, so for example, if you look at this sentence, there is something called interesting. Like, so interesting was a word, but the stem of interesting is interest. So it's basically like showing the stem of all the words that we have. Right? So I don't know. So yeah, so I guess yeah. So the first question, like why we still have dot, is basically we are not printing the we are not doing the operation on the results for results basically. So we are doing, if you look at the stemmed this line, you'll see that it is doing operation on the tokens, which is basically the first one. Yeah, so the other question is like interest could mean two different things. Yeah, so yeah, I think like yeah, I don't know how to answer that question, but basically in this case it is showing the stem of all the words that we have essentially. Yeah, the hydrogen tool. Yeah, I haven't used it so far. Yeah, thanks for the suggestion. I'll check that later. Hydrogen. Okay. Hydrogen tool. That's cool. Okay. So let's look at the other example. Okay. So what is the next topic we have? So Yeah, so we can yeah. So Peter suggests that we can maybe use Jupyter Notebook. Yeah, we actually, I think we should do that from next time. Yeah. So okay, so now we'll see like okay, what are the things we can do with SciKit Learn. So I mean we can do a lot of things, but so one of the like there are like different types of like text preparation. So I think the most common is basically people just want to like do some type of count. So we will not look into only count. I think so there is a library called countVectorizer. That's also it's actually part of SciKit Learn. We will not look into that. I mean you can look into this reference that I have. This link actually has good explanation of some of the concept that we are discussing in this file. So you can look into that for reference. Yeah. So I think one common concept that keeps coming is basically tf-idf. So tf-idf is basically it's counting the frequency of the words that you have in your document, but it also takes consideration of making sure that it doesn't take the role of stop words basically. So because in a document you have a lot of stop words generally, right? So if you want to count frequency, those stop words will be like more frequent, right? So that's not it doesn't give you an idea about what's going on in the document, right? So that's what basically tf-idf does. It takes the inverse of those words. So essentially, it negates the impact of stop words. Yeah. So for example, if we look into this text and first, so what will happen is you can like if you use this tf-idf vectorizer, then you basically get that object, and then you actually you build the vocabulary by passing this input to the fit method, and then if you print the vocabulary dot vocabulary underscore, you see the score for the vocabulary, and then if you print dot idf underscore, then you see the score of in those stop words, basically inverse score. So if we run this, yes. So what are the things it is printing? Basically, so if you look at, there are like three print statements. The first one is basically it is scoring those. It is scoring the words in the document, all the words, and then it is scoring. It is showing you the score based on the tf-idf. It is showing you the score based on the IDF. Basically, and you're saying something? Hello? Okay.
We can hear you.
Yeah. Yeah. So okay. Yeah, no problem. Yeah, and the third line is basically the shape. So the shape is it's interesting. If you look at the input, it has like key things. and they're like separated by comma. So the first three actually means like how many you have, and 12 means there are in total 12 vocabulary. So if you count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, it has like more than that. I don't know why it's saying 12. I think it is not, this is, yeah, for example, yeah, so, okay, there are 12 distinct tokens, okay. So, for example, if you look here, there is no A. So, for example, so this is, there is no A, and then virtual, NLP, study. Yeah, so basically there are 12 distinct tokens. Okay. Funny, how do you say your name? Funny? Okay.
Yep. Essentially, there are 12 distinct tokens if you count the number of words across all the documents. So, which is why the vocabulary dictionary contains each word is given in integer index. So you see the 2 is 0, the group is 1. Similarly, the will is 11. So all the words in all the sentences are mapped from each of these tokens to a particular index, which is why when you convert a document, in this case a sentence, so you have 3 sentences in your text, so essentially you have 3 documents, which means to say when you convert it to a tf-idf, you get a matrix with 3 rows, which are 3 sentences, and you get the 12 columns, which are the vocabulary size. That's the explanation.
Okay, so the column is why is the column 12?
Because the sentences are mapped from their input space to the index space. So the index, as there are 12 words in the whole vocabulary, now you have a 12 column matrix, and in fact, for the first sentence, as there are 1, 2, 3, 4, 5, 6, 7 words in the first sentence, you will have 7 of the first 12 row activated out of the 12 elements in the first column. If you actually print out the vector, just print out the whole vector. Instead of doing vector shape, just print out the whole vector. In that case, you'll actually see that 7 of the 12 elements are activated. For the second sentence, only 3 are activated because the second sentence only contains "we love NLP," right? So only 3 elements of the 12 are activated. So something of that.
Yeah, so I guess like okay, rows is number of sentence, column is number of words in vocabulary.
Right.
So
right.
yeah, so I guess like what I'm not getting is like how the vocabulary is defined, because there are not 12 words, right? So okay, let me change. Let me change this. Right. So yeah. So for example, okay.
So this is a sparse representation. If you just do dot to dense, I think you should actually see the whole result in a matrix form.
Okay, so like dot dense, to dense, okay. Okay. So what does this actually mean? So this one is, so basically there are three portions because there are three parts, right? Yeah, so I guess yeah, so okay, so this is tf-idf matrix, okay. So how do we explain this? Like, I guess it's not clear to me.
Yeah, so as there are 7 words in the first sentence, you see that in the first row, 7 elements, 7 columns are activated. The second value, the fourth value, sixth value, 8th, 9th, and 10th, right?
Yeah,
Those
yeah.
correspond to the words present in our vocabulary. Now, if you see
Okay.
the second row, only three elements are activated, which is the 5th, 6th, and the 11th.
Yeah. Yeah.
So each word is essentially given a tf-idf score, and this particular score is activated in the corresponding column in our in the whole column space of the vocabulary that we have. That is how this matrix is created.
Yeah, I guess like this like 3 of them are activated or 7 of them are activated. That part I understand because like that's like, but I guess like my question is like, if you look at this, like there are in total 1, 2, 3, 4, 5, 6, 12 items. So that's what I'm not getting. Like why there are 12 items?
So there are 12 distinct words in the whole in the vocabulary. In the text array that you have, if you count the number of distinct words you have, that is 12.
Okay. Oh, distinct. Okay. So basically, for example, okay. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah, B is already there. Will is not there.
We already have. So
Will is
11, 12, 13, 14.
Oh, so if you just remove the...
Then E's and A is removed basically, right? So if you want to count 12, like I understand that we have we twice, so we count we only once, right?
Yeah.
Then it's 14. So that means they are not using E's and A.
E's is there in the vocabulary. If you see the dictionary, is the index of E's is 3. Just see the dictionary above.
Yeah.
A isn't counted, and
A is not counted. Yeah.
Something else that isn't counted.
So here everything is counted. This NLP is not counted. Oh, okay. Okay. So okay. We have NLP twice. So
yeah.
Okay. So basically, A is not counted. That's the only thing that's not counted. Okay. So I guess then my question is why A is not counted. I mean, what is the explanation of that? Because no, I don't think that, because easy is also a stop word, right?
Yep, you're right. Not too sure about that.
Yeah, I don't know what is the explanation of that. So, okay, we can write down. Okay, so I don't know why A is not counted. So that is unknown to me. Okay. I guess I don't know, like so like, is there anything else we can explain in this code? That's my question. If not, then we'll move to the next one. Yeah, let's move to the next one. We need to have much time. So the other topics we have is basically essentially like bag of word model and word embedding, right? So bag of word, I'll not talk much about that. So basically bag of word is essentially like any count-based model where you actually count the word frequencies, and it doesn't take consider. I mean, it basically throws away the order of the words. So it only cares about count and it doesn't care about the order. So that's a problem. So for example, what we discussed so far, like the countVectorizer or tf-idf, they are actually bag of word models. But like as you understand, like if you want to do like semantics, then the order matters, right? So that's where basically the word embedding comes. So in word embedding, you actually look into the so basically in word embedding is the process where actually it takes consideration of the words, nearby words essentially. So I have a link. Let me find that link. Okay, give me a second. I have a link to where they have a good okay. Yeah, so there are some resources that I put together. So I'll share these resources with you guys. So this is one of the. So I don't know if you guys have this book, Deep Learning for Python. So they actually have the code in a notebook in a GitHub. So they have one. With respect to the text, they have this is a good example where they talk about essentially the word embedding. So basically so there are like two ways. I mean, I guess there are many ways, but I think the two well-known ways are word2vec and Globy. So you can actually create word embeddings using those techniques essentially. So here, I think they are showing, like they're talking about like how using Keras, they're actually loading the embeddings. So I think they're loading the Globy here, and so there is. So for example, if you look at this section, so there, yeah, I think we should look into this putting it all together. This is actually a good example of like what are the things they're doing. So some of the concepts we discussed, like tokenizing. So they're doing that with Keras here. So you'll see that, and then they actually loaded the Globy model here in this example. So this is a good example if you want to look into this. I don't know how. So I don't know, like you guys know like how much this model is used these days, or like. Can you guys hear me? Hello? Okay. Yeah. Okay. Mm-hmm. Okay. Yeah. I have seen that word to bake is used more than Clovey. I don't know. So I guess like what is the difference between? So they both are generating word embeddings. But I guess like my question is like if you want to say like what is the difference between word to bake model and Clovey model, right? So I mean I want to learn that. I don't know that. So do you guys know? Yeah, I guess I don't know. I mean, there's a silence, so I'm assuming that you don't know. So, um, so this is one of the example. Like, if you want to use Globy, then you can follow. There is okay. So the other thing is, I think somebody mentioned that maybe we can look into Gensim and Spassy. So if, I mean, in Kera, I mean, if you look at, so if you want to load the word to, if you want to use word to wake, basically you have to use Gensim library. So I haven't seen anyone so far using word to wake without Gensim. So I don't know why that. So is Gensim the only library who has word to wake implemented? So I don't know that. But like wherever I go, like I have seen examples like they're using Gensim library and then doing that. Yeah, so if you are using word to bake, basically like you have to do this like from Gensim models, like you import this. Hey Raja, what do you mean by predictive model versus count based? I don't understand that.
So what WordToWake does is it basically tries to predict the words. It tries to minimize the loss, like on the basis of the target word and context word and everything. It takes some bag of word model or a skipgram model and it tries to predict the next word. It tries to minimize the loss of occurring the word in that similar context. That's what it
Mm-hmm.
does. And in Glow model, what they do is they just use the co-occurrence matrix and dimensionality reduction to get the dimension of that particular word out of a
Mm-hmm.
vocabulary. So that's what they difference basically.
Also, you're saying that Globy still takes it basically
Glow
uses
uses like dimensionality reduction and co-occurrence matrices. That's what it uses. And word2vec works on the bag of word model and scriptgram, and it tries to predict the target word out of the context word and vector. It basically minimizes the loss function word2vec.
okay. So I guess like my question is like okay. So yeah, I think there are some interesting questions. I do not know. So
Hi, Nahid. I just want to add something here.
sure. Go ahead. Yeah.
Yeah, so Word2Vec has these two kinds of algorithms. One is continuous bag of words, which is like it tries to predict the center word. Let's say you have a sentence. The cat jumped over the table. So if you give it a sentence like the cat over the table, it tries to predict the center word called jump. So that is one thing. And the other algorithm is called skipgram. Okay.
Skipgram, yeah.
Skipgram, yeah. What it does is it takes a center word and it tries to find a distribution of words around its context. So word2vec is it's basically used for word similarities, as per my understanding. And Glove is like it has many other uses like analogies and all that. So yeah, so that's what I wanted to add.
Okay. So there was another question that whether this is supervised or unsupervised. So Nisa is saying that they both are unsupervised algorithm. I do not know that. I mean, I can't speak for that. So, Nisa, can you talk about that?
They are kind of supervised because they take a lot of sentences which already have the full form. Like as I said, in the case of the dog jumped over the table, you will be giving the model the entire sentence. It takes each word as a center word. It kind of starts with the first, or leave the it starts with dog, and it tries to predict the words around it. Like that, it goes to the word jumped. So by the time it reaches jumped, it has some kind of word information with the prior words. So it kind of uses that and generates some kind of a word embedding for the word jumped. Yeah.
Okay.
Yeah, word2vec is just a shallow neural network. Like there are only few hidden layers in it, and it tries to minimize the loss by using a particular loss function. That's why it's a supervised algorithm. We can see.
Yeah.
And in
I think to say brief, I think Jeremy actually mentioned this that this word2vec is like shallow learning, something like that. So and it's I guess it's he didn't recommend using word2vec. I guess I remember he said something like that.
Yeah, that's
Okay.
It needs some training data to train the phone, like to get those vectors. It needs some training data to get those vectors.
Okay. I think they mentioned something like that, and I need to look that back. Thanks, KJ, for the note reference. I'll take that. So I think I'll copy paste this chat note also and share all those things that we just discussed today. So I mean, do you guys have anything else for today? I think we talked about things like briefly today because I didn't want to spend too much time on word2vec or Glovi because I think the direction we're going is definitely will not, as Jeremy mentioned, it's I mean, we have to use like newer RNN text techniques to do things. So. Can you guys hear me?
Yeah, we can hear.
Okay. Yeah, cool. Suddenly there was a silence. So I guess like, if you guys have anything, so I'll share the material and the references, and I'll also share them on the Slack so that like anybody joining late or anybody who hasn't signed up for the email also looks into the Slack also. So I do not know. I don't know if anybody wants to. I mean, if there's anyone who wants to join, that would be great. but I don't know who wants to join. I mean, the Slack channel, I think I'll share the invite. So John, have you signed up for the email? So then I think I'll send the email again with the Slack invite and the notes from here, so then you'll get that. Yeah, and Rajat, the topic for next week, I'll share that in the Slack channel. Okay? Yeah. I don't know how to copy the chat. Yeah. So, yeah, thank you, guys. Yeah, I'll see you next time. Bye.
Bye. Thank you.